So here's our quick look at the calendar. Today we're talking about lines of best fit. After that, we have one more class about lines, and then we have our quest number 2, which is coming up on the 26th. What day is that? Is that Wednesday next week? Is that right? Yeah, so next Wednesday is our second quest, and the quest will cover the classes 6 through, well, 11 didn't really exist, so 6 through 10. Any questions on the calendar? Okay. Then let's jump in here to page 50 in the big packet. And we'll start with Victor. Could you read number 1, please? Thank you. Morgan, number 2. Okay, so let's take a look at this table and make sure we're clear on what it represents. So back in 1982 is the first year that we have some data I'm presenting. And in that year, so of all the deaths that resulted from car accident, 57% of them were related to drunk driving, to alcohol, okay? And then if we flash forward 3 years to 1985, that number was down to 51%. So about half of all the deaths that were caused in car accidents that year were caused by drunk driving. And so you can see in the first column, time is passing. Looks like we have data about every 3 years, although in the last one it was only 2 years. And what's happening to the numbers in the right-hand column? They're decreasing. Like we can just look at that and say, okay, these numbers are getting smaller. But I want to be able to say more. Are they decreasing at a fairly constant rate? Like every few years, the percentage goes down by 4%, but it's always 4% every couple of years. Is it going down slowly and then faster and faster? Is it going down fast in the beginning and then more slowly? Is it something more complicated than that, where maybe it goes down slow in the beginning and then fast and then slow again? There's a lot of different ways that numbers can get smaller, and it's really hard to figure out more than what we just said, where they're getting smaller, by only looking at a chart of information. So we're going to rely on a graph instead. So let's take a look down here, and where's our next reader? Lauren, can you read this to display part? Right. Okay, thank you. So lots of vocabulary that maybe will look familiar if you came from our Math 095 introductory algebra. So one little typo I made. In the beginning, I said P is the number of fatalities. It's the percent of fatalities, same as it was in the table. So we've got our independent axis down here on the bottom. That's time. And then our dependent axis is the vertical, the percent of fatalities that are related to drunk driving. And so I claim that all of the points that are up there are just plotted down here. So for example, let's fill in the coordinates at point A just by looking at the graph here. So what's the first coordinate of point A? Is 8, and then the second coordinate is 50. Now, looking at that 8 and that 50, can you find that point in the table? What is 8 really representing in the table? Is really representing 1988. Right. And so what that says is that in 1998, 50% of the fatalities from car accident were alcohol related. Now, point B is harder to just grab the coordinates from the graph, but we don't need to. We know that this is one of the points from the table. So looking at point B, it looks like the first coordinate is about 19. What year would represent 19 in this scheme? It would be 1999. So you can read the 1999 data from the table, which is going to be more accurate than trying to estimate from the graph. So this is the point 19, and then according to the table, 37. Okay. And so this whole thing right here is called a scatter plot. I'm not sure if this is sound, but for me, it seems like the points are just kind of scattered up there on the graph, and so we're plotting them, and we call it a scatter plot. And this gives us a lot more information than the table. Well, I guess it's the same information, but it's easier to read information from my perspective. Definitely, I can see the decreasing trend, right? The numbers are all getting smaller. But I can say more than that. I can say, okay, it looks like it's roughly linear. It's not going to be perfectly on a line, but somewhat on a line. But I can also see that, for example, the decrease here was a lot faster than the decrease here, right? It went down steeper in that first time interval than the second one. And that's immediate from looking at the graph, whereas if I just had the table, I would have to start doing some subtracting. What was the decrease? What was the percentage decrease there? It was 6% down, and then here, 1%. And it's not as obvious, right? If you have the visual in front of you, you can see when it's changing fast and when it's changing slow, as opposed to having to do all this work to analyze some data in a table. Okay, let's come down. Let's see, we've done A, where we labeled the coordinates. Part B, who's our next reader? We'll go to Alex up here. Okay, so then I think we've already established yes. As time passes, yes, as time passed, the percent of fatalities did what? Decreased. But we're going to be after something more specific than that. I would really love to be able to come away from this with some kind of a sentence like, every year, the percent of fatalities decreased by about 2%. Every year, the percent fatalities decreased by about 2%. I'm making up the 2%, but I would love to be able to have something really concrete, more so than just saying the data is decreasing. So that's what we're after. Part C, Brandon. Okay, so what I'd like you to do is use a straight edge if you can. Somebody can use the green folder on the table, or use your calculator. Use something straight to help you draw a line. And there's no line that hits all of those points, but you're going to try to draw the line that you think comes the closest to all of those points. Okay, so there's my line. It will look similar, but not exactly the same to your line, right? We have all different lines up there. Hopefully you just drew one where some of the points are below the line, some of the points are above the line, but it's pretty good. The points, none of the points is really far away from the line. What did you do over here?
It looks pretty much
excellent. Okay, next page. Number 3. I will come up here to Alan. Okay, so that's just a couple of vocabulary phrases there. Abby for A. Mm-hmm. Okay, so it turns out that there is one line that fits the data better than any other. But in order to talk about that, we need to have an understanding of statistics that's beyond the scope of this course. There's some calculus involved, also beyond the scope of this course. But suffice it to say, mathematicians and statisticians have come to some agreement about how to find the best line, the line that is closest to the data points. And it's this one. Now, how did I get it? I typed it into GeoGebra, and I'll show you how to do that in a little bit. But there is that line, and hopefully your line that you drew is something close to this line right here. All right, let's come down here to this important note. Alexa. Good. So then if your answer doesn't quite agree with what's in the back of the book when you're checking your homework, that's okay. A lot of what we're doing today is approximations. Okay, let's answer these two little questions here. For the line that I drew, the best fit line, how many points are above the regression line and how many are below? Okay, how many of those points are above the line? I count 4. You guys see 4 points above the line? How many are below? It's 3. This one over here kind of looks like, it's on the line, but if you look very closely, you'll see it's actually below, right? It would be some minor miracle if any of them were actually perfectly on the line. So I think we said 4 were above, 3 were below. And we'll go to Mariah for B. Okay, so let's look at the graph. And we're trying to figure out what's going on in 1993. No, we got to first translate because 1993 is not any of the numbers that's down here because we did some funny thing in the beginning. T started at 1980, right? 1980 was 0. So 1993 is what number? Is 13, right? Because 1980 was 0 and 1993 is 13 years later. So really we're asking about what's going on in this graph in t equals 13. So what we'll do is go to t equals 13 here. Now, is there a data point above t equals 13? No. If you look at the chart on the previous page, does 1993 exist in that chart? No. So we're trying to get information that we don't have. Any ideas on how we can use the graph to estimate what might have happened in 1993? Okay, so we'll go straight up to where it is on the line. And then we'll go straight over to the y-axis, which is the p-axis in this problem. And then we're going to estimate whatever that number is. Okay, what do you estimate? 42? 43? Any of these numbers is fine. If I had a straight edge, I'd feel a little bit better, but I'm content saying 42. So from the graph, 1993 corresponded to approximately 42%. All right, let's go to boo for the sentence right above C. Okay, and then in the back, Yurka for C. Okay, so here's the goal. The goal is to find the equation of that line that's drawn there. Now we're going to be just looking at the line, so this is all going to be estimation. But in order to find the equation of a line, we know we need 2 points. So we're going to pick any 2 points that are on the line. We're not picking 2 data points because the data points aren't perfectly on the line. We're trying to pick points on the line. So can you find any points that are on the line that have nice coordinates, that have coordinates that we could easily estimate? Somebody give me a value of t that looks nice. How much? Yeah, what value of t? I thought somebody. All right, so t equals 7. Is that where you want to go? Somewhere around there. Alan thinks 750 is pretty close to being on that line. So do you guys, would you agree that's a fairly good estimate? So it's a good point to pick. I would certainly never pick a point like here, you know, like, I don't know what that is, 20.3 and then 32, 33. Like you want to pick points that are near the grid. All right, anybody find another point that's pretty close to being on the grid? 16 and 40. You guys buy that? That one's pretty close to being right on the grid. That looks good. So we've got 16 and 40. Great, 2 good points. You could pick other points as well. You just want to pick things that are easy to estimate. But I'm highlighting again, you are not picking points that are plotted. You're not picking points from the chart, you're picking points that look like they're on the line. Okay, let's use these 2 points, 750 and 1640. Okay, so now we're trying to find the equation of a line that hits 2 points. And now this problem we can think of having nothing to do with this word problem, the context that we're given. This is just find the equation of a line that hits 2 points. And we've done that before. Definitely we're going to need to find the slope of the line connecting those 2 points. So let's give it a shot. I've started us off here. So normally we write m is, or the slope is, what? How do we pronounce that delta symbol? What does that represent? Change. So normally it's change in y over change in x. But let's use the letters that are in this problem. There's no y in this problem. What is it? Is it t or p? It's p, right? It's that percentage of fatalities. That's what we had up above. So that's a p there. And then x on the horizontal axis is now t. What numbers from these points am I subtracting on top? So 40 minus 50, or the other way. And then downstairs, 16 minus 7, or the other way. Okay, so what is that? Negative 10 over 9. And normally I leave everything as fractions because when you go to decimals, often you're approximating. But I think decimals are going to be better for us in this context. So with the calculator, if we type in negative 10 over 9, I think we get negative 1.1 repeating. Any questions on calculating the slope? Has anybody confirmed 10 over 9, 1.1 repeating? Victor, did you get 1.1 repeating? Karen? Yes, okay. All right, next page. We're now ready to find the equation of that line. Now, normally, to find the equation of a line, we're using y equals mx plus b. But let's change those letters. We don't have y in this problem. What do we have? It's p equals m. We don't have x. It's t plus b. Okay, we just found the M. What was our approximation? Negative 1.11 T plus B. And now, before we solve for B, we got to plug some stuff in. So for example, we're going to plug in, what was the first point? Was it 7 and 50? Right, so let's plug those in for T and P into that equation. So what do we have? Instead of P equals, what do we put? 50 equals negative 1.11 times 7. And then we have to solve that for the B. I got B is 57.77. Yes, no, maybe? Yes. Okay, and so then I think we're ready to put everything together and come up with our final equation. P equals negative 1.11 T plus what? 57. It is messy, and just about any equation that is worth anything is messy. Anytime there's data involved, it's messy. All right, so there's our equation. What's the slope? Negative 1.11. We're going to talk about what that actually means in the context of the problem. What's the y-intercept? 57.7. Now take a look at the line on the previous page, the one that I graphed. Does it look like the y-intercept is about 57.77? Yeah. Is it perfect? You would have said 58 if, yeah. So it's probably not perfect because we estimated. We found 2 points that we thought were pretty close to being on the line, but that should be a good estimate there. Okay, and so let's go down to step 4. I think we're back. Karen, did you read? Okay, so were we close on the slope? Pretty darn close. We're off by, what, 0.08. Were we close on the y-intercept? Pretty close. We're off by less than 1 on the y-intercept. Okay, so now let's do this analysis piece. I didn't ask us to think about what the y-intercept meant, but let's do it. This corresponds to a point. Again, there's a T and there's a P. Is that 57 the T or the P? That's the P, 57.77. How much is the T at the intercept? It's 0. So that's what the p-intercept is. It's the value of p when the other variable is 0. But 0 corresponded to what year? 1980. So then we can write a really clean sentence. In 1980, the percentage of car-related fatalities that actually had to do with alcohol was about 57.7%. Now we do have data. Do we have data for 1980 or no? No, we don't. So this is information we didn't have before, but our estimate for what was going on in 1980 is that about 57% of the fatalities in car accidents were alcohol related. So we can write that up here. In 1980, 57.77% of car, all that stuff. All right, now I think that people are generally pretty good at identifying what the intercepts mean in context. So that kind of a sentence, I think most of us would be able to just come up with without too much difficulty. But the problem arises down here in part E, where I ask you questions about interpreting the slope. What does the slope of the regression line mean? And we're going to try to write a sentence in plain English. We want to interpret that slope, that negative 1.11. So before we go with that, I want us to take a step back on the previous page at the bottom and think about what the units are. So here at the bottom is where we did our calculation and we got the negative 1.11. But let's think about where it came from. Upstairs was a change in P. Downstairs was a change in T, right? What were the units for P? It's percent, right? Those numbers in the second column of our table are all percentages. What are the units for T? Years. All the numbers in the first column were years. So upstairs is a percent, downstairs is a year. So I'm going to write that over here. That's a percent over year. And I'm really going to force it to be a fraction by putting what number on the bottom? 1. Lots of 1s in this one. So in terms of interpreting that number, I'm just going to first read it with the units, and I think that will be just about all we need to do to interpret. Negative 1.11% per 1 year, or negative 1.11% per year. Okay, so here's our sentence. The percent of fatalities was so we could just say changing at a rate of negative 1.11 blah blah, but let's get rid of that negative and write a different word other than changing. Decreasing, right? It's changing in a negative way, so it's decreasing. Was decreasing by about 1.11%. What were the units again? It was percent over years, right? But that's not a plain English way of saying it. What's a better way to say it? That's perfect. Each year, the fatalities decrease by about 1.11%. Victor? So the negative, we have taken it out and put it into the word decreasing. Instead of saying each year in the front, I'm going to say per year at the back. Either way is good. And this is what I was after way back in the beginning of class. I wanted something really concrete that we could say, well, what was really happening in terms of how the percent fatalities were changing? Sure, they were decreasing. But after all this work, we finally have something concrete. They were decreasing at about 1.11% per year. Is that a perfect estimate? No. They didn't decrease by 1.11% exactly in any year. But this is the best estimate we can get to incorporate all the data that we're given. Okay, this one says use the regression line to predict the percent fatalities due to drunk driving in 1988. You know what, I want to do one that we estimated before. Which one did we estimate from the graph? 93? Let's do that one instead. What value of t are we talking about for 1993? That's 13. And we now have not just we're not going to look at that line like we did before, we're actually going to use the equation that we worked so hard to get. So I'll write the equation again here, which P equals negative 1.11t plus 57.77. And what do we need to do to answer this question? Plug in 13 for t, right? We're just trying to find the percent. We're trying to find the p. So let's plug in the t. Somebody with a calculator will help us out here. How much? 72.2. Oh, yeah. Did you type in a negative at the start? That 1.11? And then you add that to the 57. Right. So it's gonna be smaller than the 57 because it was a negative 14. So what did we get, Victor? And then add the 57.77. Morgan, do you have this? Who? 33.34. Okay. So this is really the most accurate answer we can give to the question, what was happening in 1993? Well, we're going to estimate it was about 43.34% that year. How does that compare to the estimate we got from the graph on the previous page? Yeah, what did we say from the graph? We said 42% from the graph. So this is more accurate because we're using an equation as opposed to reading something off of the graph. If we really wanted the most accurate thing, we probably should have used this guy, which is the equation that GeoGebra gave us, which is the perfect equation for that line. But our equation was good too. Okay, since we used the regression line to estimate or predict between known data points, that is to say 1993 it wasn't in the chart, but it was between the ends of the chart, then what we just did is called interpolation. But if instead we wanted to use the line to predict what was happening in 2002, you guys see this is after the last piece of information in the chart. So this is something different. Interpolation is when you go between the known values. And our vocabulary word for going outside the values is extrapolation. Okay, so what are we plugging in for 2002? How much? 22, right? 1980 is our start point. Okay, so let's just go ahead and do the same thing, but we're plugging 22 into our equation. Okay, anybody have a number for us? 33 point. Thank you. And that's reasonable looking at the data we have. It continued to decrease and it got a little bit smaller by 2002. Generally speaking, would you feel more comfortable using a line of best fit to interpolate between the data points or extrapolate something outside of the data points? Which one do you think is safer in terms of estimating? Between or outside? It's between. There's a danger in using the past to try to predict the future. And in fact, we don't need to read this whole paragraph, but it turns out that that decline in percentage actually kind of stalled in the years following the data that we have. It said in, what we have here, it says in 2002, there were actually more alcohol-related deaths than in 1994. And the alcohol-related crash rate actually has declined only a little bit since the early 1990s. So it hasn't changed by all that much, which means that the trend that we saw did not continue. And so that's the danger in trying to predict the future from past data. Okay, we have, what do we have? 35 minutes. So the group activity is in the book. I think that 35 minutes is more than enough time to get that done. So if you finish that early, you can get started on homework, or if some people are trying to still figure out what was happening in the last class's lesson, you can go back and ask questions of your neighbors or me. So let's see how far we can get in the time that we have left.